Ladies and gentlemen, welcome back to our papers this afternoon. So we've got two left, and I believe both of these are interesting. Cornelius Gould. He's an audio audio algorithm architect. He's working for Angry Audio. He's also Cornelius's background in audio processing began when he was a teenager around 1986. So he's been in the business as long as I have. There you go. There you go. With his basement FM radio station, his main observation was that of the radio stations on the dial surrounded livelier than his. The answer as why he proved to be quite a mystery. One day, the stepdad of one of his friends mentioned that radio stations use a device called an audio processor to make their songs sound louder than they really do. The aha light bulb went off in Mr. Gould's head. Ladies and gentlemen, Mr. Cornelius Gould.
Hello. Today we're going to be talking about something that I've been involved with in the latest round of processors I've been making for Angry Audio, and that is loudness normalization, and we're going to go into a little bit about LUFS, which has been in the industry and talked about more and more. And this presentation here is a little more radio focused than the TV stuff, but the TV idea is similar, and I'll tell you where the similarities are. So, like they just said on the presentation, there's pretty much a lot of what I had in here that, been engineered CBS radio for a long time, been at Telos twice. One is customer support, and then I returned later in the 2008 or so in R&D, where I worked with Frank Foti to develop the Omni 11. And from there, I went on to do other things and turn up in Angry Audio. I've always had a passion for streaming new media, whether it's podcasting or music programming. And so a lot of my processing has been evolving around that space. And so today we're going to be talking about what's LUFS. And we're going to be covering how useful it is in the day-to-day setting of your plant and ways to measure loudness for different for streaming or in your plant. And we'll talk about using the right meter for the job. And so that's going to be a lot of fun. And what we're going to start with now is I've decided that a few weeks back that I'm going to start this whole discussion around normalization, which is where LUFS normally gets used in podcast delivery, song delivery. But it really gets at the point at what it is, because a lot of the confusion with people is what is this LUFS and how do I measure it? So I'm going to start with normalization as most radio people have come to know it since the 90s, and that is with peak normalization, which is what most of the production people think of. And we want to normalize our library, so they want it to look like this. And when you do that, yeah, the peak levels are all the same, but the loudness isn't. And for anybody, for engineers in the room, which is most people here, you know why. Because the song on the right is smashed down with audio processing and compression, and the one on the left is not quite as smashed. So the one on the right is going to sound a lot louder, and you can normalize till the cows come home to peak normalization. The one on the right is always going to sound louder. And so I have a little bit of a demonstration of that here. So we'll listen between the two songs. First song. So that was quite a difference between the two. The second song is about twice as loud as the first. And when you have that going on in your library, which we all do, especially if they're peak normalized, it makes transitions in and out of songs a little rough on the downstream processing. If you're voice tracking, which a lot of people are these days, it's pretty common. When you're trying to voice track against a song that's coming out quiet, going into loud, or vice versa, you got to play games with it. And so it just makes life a little bit tricky. So what we have here when it comes to LUFS is that the LUFS normalization is basically taking into account the subjective loudness between files and adjusting them based on loudness. And the reason I started with this is because the radio station I was at a few weeks ago, there was this debate between the engineer and the production guy. And he was like, hey, I thought you normalized the library. And the engineer goes, I did. So, but I'm looking at it, it's not normalized, the levels are all over the place. And the engineer, RMS normalized it. It's not normalized, it looks the same as it did before, everything's different. And so I'm listening to this in the background, I had to kind of, yeah, I know what you're talking about here, and this is why. So I figured this is a good place to start. So on this slide here, we have our two songs once again, and they're both normalized based on loudness or apparent loudness using the LUFS system. So, and you can see that the song on the left, which was a lot taller before, is way smaller versus the song that's not as processed. And so to the untrained person, they will think that this one is louder than that one. And it's just, no, the peaks are taller, but they sound about the same. So what we're going to do is we're going to listen to that. So with this little clip here, it's basically demonstrating what the idea behind the whole LUFS thing is all about. So no matter how you produce your material, at the end of the day, if you loudness match them using the LUFS standards, they tend to sound a lot more even to the ear. So from this point on, I'm going to talk about how that is and what this whole system is doing and how is it measuring to do this trick here. So we're going to start with another topic here that kind of starts to drill down to the point, and that's measuring your audio. Yes?
I have that t-shirt.
I always love that ad. So basically we're going to get into the way you measure loudness and how hard it is on a lot of the gear, like digital audio workstations we have now. You cannot tell loudness for the most part with the tools you've got. A lot of consoles you can't do that, and here's why. The original loudness meter was the VU meter, mechanical meter, which is one of the points, and it had a very specific characteristics. It had a 300 millisecond rise time and a 300 millisecond fall time. And the whole idea behind that is that it kind of mimicked how we perceive loudness changes and put it on the meter. And that was the whole point of it. It was a volume unit meter. And it was tied to a scale, a logarithmic scale, with this from -20 typically, and at 0 and 0 meaning your target. So this meter, used for a long time for loudness. A lot of your veteran radio people love this VU meter, and they'll tell you, recording people, yeah, I can mix better on a VU meter. I don't like these dancing meters. And you'll see that they're right, and why. The meter you usually run into is the peak sample meter, and that's on all of your digital audio workstations and all that. These are great for telling you how much headroom you've got left, whether it's on a board or whatever, because when you get to 0, you're just out of headroom, game over if you try to go over that. VU meters not so much because it's so slow that you really don't get a sense of the headroom on the VU meter. So, sample meters are great for showing you headroom, and VU meters are great at showing you loudness. One of the weaknesses with the VU meter, though, is that it's measuring the signal level as it appears to the meter. So one of the things that'll throw the meter off is a song with a lot of bass. And when you play those, the meter will show a loudness level higher than what it appears to be to you. And so that's really the biggest weakness of the VU meter. And the other one that's kind of a minor thing, but it is a weakness, is that you don't know what your peak level is. You don't know how much headroom you have on your program bus. And that's, people who are used to one or the other would knock them for, those differences. The sample peak meter, however, is great for headroom, but you can't get a clue with what the loudness is between two files because of the way it works. Here are our same two songs here on this slide here. On the left, we're having what the peak sample meter would show for the level of this song here on the left. And on the right, this is the peak sample meter showing the levels of this one. So because the peak meter is showing you where these peaks are, this quieter song actually shows up as being louder, if you will, on a peak sample meter than the one on the left, where they're both loudness matched. Now, on the VU meter I put on the bottom for comparison, you can see that the VU meter does a pretty good job of telling you that both of these songs are the same relative loudness. The only problem is that on this song here, the bass notes on this song, when it gets into the bassier parts, will cause the needle to read a lot hotter. So ideally, there should be somewhere around this minus 5 point. Take a little drink here. So, what's LUFS? The LUFS system takes into account all this stuff. And we're first going to jump into why it is that the VU meter shows you the error with the bass. The reason being is that us humans, we don't hear audio flat like the electronics does. So for the bass to sound normal and at the same level as, say, something in the mid-range zone, we've got to have the bass boosted quite a bit up. And if you run your speakers down lower, you have to boost it even more to make it sound even. So what's happening is that the VU meter is showing you that boost. Even though we don't hear it, but the meter sees it, and it shows you that. And another way to look at this on the Fletcher-Munson curve here is to flip it around the other way. If you go upside down, you see that the sensitivity of the bass is a lot lower than at the mids and high frequencies. And we kind of evolved that way for survival, The frequencies that are important to you are up here. If you're in the woods and you hear twigs breaking behind you and leaves rustling, that's not good. I'm supposed to be the only one here. What's going on? So, survival thing. Another component to loudness is time. So, a peak, which is a very short burst of audio at a high level, doesn't appear to be as loud as a longer term, loudness change. So the test that I will show you here in the room is one that drives my cats nuts every time I rehearse this. But I have a series of tone bursts here, and they start really short, and they progressively get longer and longer. And the longer these tones go, the louder they'll appear to sound to you. So there's the first one. Okay, that's loud. So that's the effect of time. Exactly. So the loudness meter takes that into account as well in the LUFS system. So if you take these basic concepts and put them all together, you end up with the basis for the ITU BS 1770 loudness meter, which is where the whole LUFS standards are kind of based on. So the first component of the loudness meter is the decay weighting filter, which is two different filters. One is a bass roll-off that kind of tracks how our sensitivity to the bass. And the second one is a little boost at the presence and highs. And I just learned today that the bass filter is called RLB, and the guy who invented that named it after his wife at the time. Something I should learn here. So the combined response of these, if I go and just do a crude erasing of these, you'll see the meters have response that kind of starts with a bass roll-off and they get a little kick at the highs, which happens to pretty much mirror the Fletcher-Munson curve. And the hope of that was to make the meters more accurate and have it track to how we perceive loudness when you're trying to figure that out. So the other component is time with this meter. So at its core, for momentary loudness, it uses a 400 millisecond rise in fall time, which is a little bit longer than the VU meter is, but it seems to work pretty well. So if you put these together, we can put together a really crude basic loudness meter where you have your bass filters, and then you take an average or an RMS calculation of the data from there, add them together, and then you give it the 400 millisecond averaging to it for the rise and fall time and convert it to a dB scale, and you end up with a loudness meter. And here I have a K meter being displayed, And in this configuration, you have a momentary loudness meter. So it's kind of like a new version of a VU meter. Now for TV, a lot of what's going on is a 5.1 surround system. So what you do is you have the same thing here, except left, right, and then left rear, right rear, and center channel. And there's a little bit of a level boost on the rear ones, and then you sum it together, and it goes to a common meter. So that's kind of like where the differences between the radio and the TV are with it. On these meters, they usually have some form of a peak level, so you know what your headroom is like. And they take advantage of what's called a true peak meter. And what that's about is a way to give you a more accurate level of where your peaks are. So here we have a true peak meter. Well, I'll give you some waves and show you what the true peak meter is measuring. So for digital audio, you're basically taking snapshots of a waveform. And the faster the snapshots are, the higher the sample rate is. So whatever it is that whatever the level is at the moment you take a snapshot, that's what's in that frame, and the next one is if it's higher, then it goes higher. So as you reconstruct it, the filters, which is kind of reconstruct the original waveform from these little points in the sampling, a peak sample meter is literally showing you the level of that peak at the moment the sample happens. So in this picture here, we have these little dots, and they represent where the snapshots are happening to represent this waveform. In your digital audio workstations, you can see that by zooming way in, and it'll show you the dots where the samples are. This picture here is a 48 kilohertz program content oversampled by 4x, so it's about 192 kilohertz. When you do that, you get a nice accurate picture of what the peaks are. And that's the basis behind the true peak, is you oversample it. And the reason for that is if you try to do the sampling, peak sampling at the sample rate, this is like at 48 kilohertz, at 1/2 of the Nyquist frequency, which is around 12 kilohertz, you end up with your waveform points may or may not hit the peaks. Sometimes you might be halfway up the waveform at best, you know, and other times it's down lower. So by the time you average all this out, draw it into a meter, your level ends up being a little lower than it actually is. Now, this doesn't affect the audio in any way, shape, or form because the digital to analog conversion with the reconstruction filters, they will reconstruct the original waveform. So it doesn't make the audio less accurate. It just makes it a little tricky to try to figure out what the peak level is using so few sample points. So for true peak, it's important to oversample. And here we zoom in where the sample points are at 48 kilohertz. So you kind of miss out on the peak that's way up here because the sample happens to be taken right somewhere halfway up the waveform or so. And that could be, at worst, about a 3 dB error. So that's important when you're streaming because you want to feed your codec with audio that's not going to overdrive on the outputs of the digital to analog converter at the listener's listening point. So true peak you'll know if you're dead on with your output level, true peak, you're going to be good when it gets decoded. So, see, here we are with the basic meter for loudness, and this is just like a glorified VU meter at this point, where you have your K-weighted measurement, true peak in there, and the scale is now in LUFS. And what that is a frequency-weighted average level of your audio. So instead of it being a VU or volume unit, it's now a loudness unit, or LU. And the scaling that these meters are on is a full scale 0, just like your peak sample meters are referenced. So LUFS is basically loudness units full scale, or LUFS. And like I said, this is like just a momentary loudness meter, so it's like a glorified VU meter, or maybe a new VU meter if you would like. So with this in mind, real quick, let's take a look at these two songs again using a K meter, and you see that they're both loudness matched at minus 24 LUFS, with the frequency correction to account for the way we hear loudness at various frequencies. you see that now these two meters show the song on the left and the song on the right as being about the same loudness. So that's the advantage to the loudness units. Now we're going to take it one step further. For streaming, you have to have a little bit more data, and you need more of a long-term thing. So the meters get a little more complicated now. So you have your momentary loudness, like we just talked about, where you go through the filters and the RMS, and you add them together, convert it to dB. Here's your momentary loudness. And then you have two other meters, and the longer you look at the audio, the longer you average the loudness, the more accurate it is in terms of the sensational impact that it has on the listener. And it's kind of like the loudness is more of an afterthought kind of thing than it is in the moment. So the second meter you usually have available to you on a LUFS meter for streaming and file work is a short-term loudness, which is a 3-second average, which means the audio will have to be at the loudness target for about 3 seconds before the meter actually shows it there, that it's that loud. And the last one is integrated loudness. Now, integrated loudness can be calculated as the average loudness of a file or a video or a movie from the beginning of the movie to the end. And it continuously averages the loudness, and by the time you get to the end, that average loudness is the loudness of that movie or song or whatever in LUFS. And that's typically how it's used. Now for streaming, we've come up with something a little bit different, and I'll show you that in a second. The loudness meter is represented in all kinds of ways. There's been pictures you saw of a little circle that was on my presentation. That's a TC electric loudness meter, TC electronic. There's also the U-lean meter, which gives you a nice little histogram of loudness over time. And what we do in our streaming products at Angry is I have 3 meters that represent the ITU loudness. The first one is your momentary loudness, and the second is the short-term 3-second, and the final one is integrated. Now, for streaming, we do something a little bit different, and I'll get to that in a second. I want to get to the one point that everybody's probably wondering about, and it's how do you measure your stream loudness on your station? So, and that's kind of, that's the one thing that's kind of the Wild West, because stream loudness measurements and all that is still kind of new. And because the key problem with streaming loudness for live stream stuff is that there is no beginning and there is no end to the programming. It's just programming that's continuously going. And if you use like a standard loudness meter with it, the integrated loudness will start off fine, but the longer you go, the lower and lower the integrated loudness will come across. You have to kind of keep resetting it every few minutes to get a feel for what your integrated loudness is. So the first thing that's key to this is knowing what the target is that you're trying to measure. So you have to, and make sure you stay on that target, as they found out here with the Death Star. And that's critical to get an accurate loudness metering. So if you know that the station you're measuring is supposed to be at minus 16 LUFS at minus 1 dB true peak, which is the ITU standard for your high bitrate audio sources, then you kind of have an idea of how to kind of gauge the meter that you've hooked up to the output of the stream decoder and kind of get a feel for it. I find it's best just to kind of measure at the output of the audio processor, because you know where the peak level is, and wherever you set it, you just kind of match it up on the meter, and you know what you're feeding into the encoder is correct, as long as if it's minus 1 dB true peak coming out of the processor, that it peaks at minus 1 dB on the encoder input. The other thing you have to keep in mind is if it's a low bitrate stream or low bitrate MP3, the codecs are not going to reproduce the peaks exactly. They're going to overshoot. So you'll have to kind of back off on your output level a little bit to compensate for that. So there might be 2 dB or minus 3 dB, and you compensate the loudness around that. So these are things you have to keep in mind when you're doing that, when you're measuring off of a stream decoder. So, and that's just what I just talked about there. So now for stream loudness, for what we've come up with integrated loudness measurement for streaming, and it's not an original idea because Orban does the same thing with their streaming loudness meter, is we come up with a concept of a rolling integrated loudness. So in the work that I've done, well, I'll get to that in a second. Here, I'll show you in this picture here. Since you have no beginning or no end, what you want to do is you want to set up some period of time where you're measuring integrated loudness. I found that about 30 seconds for a live stream is kind of a nice little sweet spot because of the way audio programming works. So basically what the processor does, it makes a 30-second buffer or a window. And as the buffer fills up, the previous 30 seconds just starts to fall out of that window. And in this example here, the target is minus 24 LUFS. So the integrated loudness is measuring in this 30-second window, and for every 30 seconds of audio, you kind of know whether or not you're pretty much in the ballpark or not. And at that point, no matter how you measure it downstream, or if you have some regulatory agency or whatever that wants you to hit a certain, integrated loudness, that will, that no matter how they do it, it's going to measure correctly. And so that's been the solution we have. Orban's is adjustable, so you can go from 10 seconds to hours if you want. And basically, the rule of thumb that I have is if you want something to be dynamically pure, then a longer window is what you want to go for. And I don't really recommend going shorter than 30 seconds because then that forces you to kind of smash the audio unnecessarily, because the shorter the time period is, the more you're going to see variations in loudness, and it's going to force you to crank on things to try to make it sound more uniform. So as we wind down on this thing, and I hope, kind of gave some insights. Right now, for streaming loudness, and this is a discussion we had before I got here, it's kind of an evolving thing. So the only standard right now that there really is, because there is only one standard right now for loudness, and that's for, in the US, television, using the Column Act. So TV in the US has to be at minus 24 LUFS loudness. And streaming services are kind of sort of in that ballpark. Netflix is at minus 27, and they go lower than that because they like having the sound effects stand out. For this explosion, they want to have maximum boom to scare you out of your room. Europe is a little bit different, minus 23 LUFS, and they're under regulations as well. Sony is in its own little world with video. They're at minus 18. YouTube, YouTube is video, and I would think that they would be at minus 24, but for whatever reason, they're at minus 16, and which is kind of loud for video, especially if you're coming off of Netflix and you go to YouTube TV, and they're just like blasting you in the back of the room. Commercials are louder, but if you have a loudness level, it'll bring it down. Where it's not that loud, it'll pull it down. Podcasts have all voluntarily sat around minus 16 LUFS. And that audio, or any of these, if you're doing mono, you want to be about 2 to 3 loudness units lower than stereo, because when you have the same thing coming out of 2 speakers, it's twice as loud as when it's diffused across the 2. So that's like a compensation thing. And if your processor or your measurement tools do not allow you to differentiate between the two, the sweet spot, if you're doing mixed programming stereo mono, is to be somewhere around about minus 18 LUFS actually. So it kind of shows you the little snapshot of the world as we speak right now. And it's moving, it's always changing, and whatnot. So some important things to keep in mind. If you use LUFS-based loudness measurements to normalize your music libraries, then that will create a much easier environment for you to work with on the staff. Your commercials and your music will be reasonably balanced with loudness-wise if you do that. Much easier to voice track in and out of commercials and songs and sweepers and things like that. And if you're measuring for your live stream, know what your targets are, and make sure you really are measuring the LUFS accurately by getting all the levels right and making sure that you're aware of all of that. So thank you very much for that. Hope that was clear. Feel free to ask any questions. So. Yes.
In the mastering world, normalization meant boosting the gain of the audio file so that the peak was a 0 dBm full-scale signal,
Mm-hmm.
maintaining the dynamic range of the audio. I was surprised to hear that same phrase used in radio as a method of compressing the
Oh.
audio. Is this like a standard practice for radio?
Is for going for 0 VU maximum. I think in radio, yeah, I wouldn't say it's a standard practice, but people tend to go for 0.
No, I
Oh,
understand.
okay.
But if I have a recording where my peak, the overall file peak is -7 relative to full scale,
Mm-hmm.
you can boost everything by 7 dB, not cut your peak level,
Right.
and maintain the dynamic range of the original content.
Right.
But that's not what you basically stated in your first few files. I mean, the examples that were, the examples.
Oh, okay.
Your peak normalization.
Right.
And you were actually compressing.
Oh, no. Oh, okay. So there's no peak, there's no compression, but what the peak normalization does in that case is that whatever the highest levels are, it makes that, it's, let's say 0, or if you're going from -7, it'll bring up to -7. So that song so they're both at the same reference point, which is the idea. But if you match up the peak levels, if one is processed in mastering to sound louder than the other, then it's just going to sound louder. So, yeah.
Now, it was a little confusing because they were two completely separate audio files.
Right.
And so one of them, okay.
Yeah, so one was an older master, basically. The way, there is that song was remastered because it does have, you can see that the peaks are shaved, but not to the point that they do it now in a modern day top 40 release where they just buzzsaw everything off and then turn it up. So, yeah. Oh, thank you for the question.
Corny, you had a screen where you had like 2 meters. And I think it was kind of like brown sort of colored audio that was running. One was running like neg 22, and the other one was running like neg 25. And I was just wondering if that was no, it was further on towards the end, I think. And I was just wondering if that was more like, is a LUF the same as a dB? So would that 3D, that 3
Okay.
LUFs make an audible difference to us?
Yes, the scaling of LUFS is scaled on a dB scale. The main difference between the two is that the LUFS, or the loudness unit, LU version of that, is frequency weighted to compensate for your sensitivity between lows and highs. So, but other than that, the scale is almost is basically like a dB. So if there's a 3 dB difference between the two, then the one is still going to sound twice as loud.
Okay,
as the other
thank
one.
you.
Yeah.
What's the, is there a free meter?
A free meter?
Software.
So what's the goal that you're trying to accomplish?
Monitoring streaming levels.
Okay. For monitoring streaming levels, Orband's loudness meter is free, and that's the one that has the rolling loudness window that you can adjust. You can also use the Ulean meter, which is free, which is useful for that. You just have to keep in mind that you may have to hit the reset for the integrated loudness every couple of minutes or so.
Okay.
So.
Anybody else? Hold on, Will.
We used to adjust our audio to -20 LUFS, and we assume that this is 0 BU. Are we correct? I said we used to adjust our audio level tone at -20 dB or -20 LUFS.
Okay,
DBFS,
okay.
yeah,
Okay.
DBFS, and we are assuming that this is 0 BU. Is that correct? Is that a correct assumption?
A lot of it's going to depend on exactly what your reference is, but where. Now, what's the meter? Is it like a peak meter or a VU meter? That's going to be the
We are using Wardbeck, you know.
Yes.
Yeah, we are
So-
using Wardbeck, and we are sending a tone.
Okay.
Usually we are sending the 5.1 tones. So we are sending 8 tones. 8
Okay.
tones simultaneously,
Okay.
and we set them to minus 20 dBFS.
If it's reading peak level and you set it to that, it's going to be kind of in the ballpark there, but it's going to be. But as soon as you play audio through it with peaks and all that, you're going to lose that reference because the peak meter is going to read those peaks as a lot higher than what you're feeding. If it's VU ballistics based, it's going to be sort of in that ballpark, and it may or may not be exactly there because it doesn't have that frequency weighting, but it's kind of going to be in the ballpark. What you might want to do is to have one of the TC electric meters on the meter bridge connected to your program bus. That's going to give you a more accurate picture of what LUFS is versus any kind of a meter that's working in the flat domain.
Yeah.
So
That was the engineering point. However, our audio man will adjust the audio the way he wants it, you know,
got it.
using the LUFS.
Yeah.
Anybody else? Okay. Corny, just my curiosity question is about commercials in television. So I get people complaining to me that the commercial sounds really loud and the program sounds low. And I know that I'm running both of them at the same levels. Is it because of the frequency response in the commercials, or is it because of the lower frequency response in the program?
It is more to do with how dense they make the commercial. So, and I'll use this slide as an example.
Okay.
So the commercials are going to be produced, most of them are going to look something like this.
Right.
And your program is probably going to be a little bit more open
Right.
than that. So what we're hearing is this middle part here.
Right.
So in the commercials, they clip off all the short-term things that we don't hear and just then turn up the middle.
Okay.
So that's what you're really hearing is a difference in the loudness. And this is more of a time-based thing. So because the time spent at the high points on this is a lot shorter than here.
Yeah.
So that's where that time thing comes in, where you're hearing the commercial is louder because it's dense for a longer period of time because they're using processing.
Okay.
So a loudness meter would show that, and you would turn down the commercial to match it, and then it won't sound as
Yeah, and
loud.
we're using an average meter, not an actual peak
Right.
on there. So
Yeah.
Okay.
So.
All right. Thank you. Corny, thank you very much. On behalf of the CCBE, I want to thank you very much for coming.
Thank you.
This is a gift for you to take and enjoy.
Thank you.
I'm just going to
Oh,
take
fine.
a picture with you.
Thank you.
Appreciate it very much.
Hope you enjoyed the presentation. I hope it made sense.
Thank you very much.
Oh, you're welcome.